Well, it's up to you.
Ring it. Wait 30 seconds?
Yeah, it says wait because that just allows everyone to get into the room.
Okay. I have my watch on.
It's probably fine now. Ring the bell.
Okay.
Well, it's my pleasure to introduce Taylor today. So for the introduction, I'm going to show a little preview for The Making of a Scientist, the Taylor story. So Taylor had an interest in science that probably started at a young age. I could only track down photos from her undergrad, so that's where our early explorations are starting at. So she majored in, or she got a degree in wildlife science and environmental science at the University of Idaho. And after that, she did a Fulbright where she went to Denmark and actually worked with people I work with and that I'm going to go see next week. And then she spent some time in Greenland. So when I was looking for a student to work on an emperor penguin project, I was like, okay, this person has spent some times in the polar regions and would be a potentially good candidate. So before heading to the Antarctic, she needed to develop some survival skills. So things like rock climbing. I was like, okay, I'm not quite sure how useful that will be in the Antarctic when we're working on flat ice. But it was quite useful for climbing up all of the ladders to get to the ice tower. It's also really important to be able to find food. And so she showed good signs or developed good foraging skills throughout. And then she also had the capability of finding important watering holes. So after all of this training and developing these survival skills, she was ready to head to the Antarctic. So our field mission was to head to Antarctica, and that took actually quite a bit of travel. It was at the end of the COVID days, and if we got COVID, our project was canceled. So we spent 36 hours basically wearing masks as we traveled from San Francisco to New Zealand, where we then had to quarantine for several days before we finally got to fly to Antarctica, where we then had to quarantine for several days before we were finally allowed to take our masks off and get onto the ship. So lots of travel, but we finally got onto the ship. Then we had like 20 days of going back and forth in the same region. And then we finally got to head over to our extreme environment to capture emperor penguins. And so she'll be talking more about the penguins today. In addition to working hard in the field, she was always up for having fun, even after long hours in the lab, clearly sunbathing on the ship when we were still stuck on the vessel. So we got to New Zealand and we weren't allowed off the ship yet. So there she is celebrating her birthday on the deck of the ship in New Zealand. And then, wearing ugly sweaters at our annual Christmas party. And all of that hard work paid off. She received numerous awards as a student here. She received the NSF Graduate Fellowship, CSU Coast Award, the CSU Program for Education and Research in Biotechnology. She received several Moss Landing Awards, WAVE and JEDI, and then also an SJSU Viola Palmer Scholarship. And while she was here, she participated in 2 different conferences, the Marine Mammal Conference and the International Whaling Commission. She's already moved on to her next adventure, so she is currently a PhD student in the Ocean Ecology Lab, so I'm sure she is quite excited to be finished with this degree and just focusing on one. And I'm sure in a few years we will see the sequel where she is a PhD or a doctor, Dr. Taylor. So with that, I will pass it off to her, and she can tell you all about her research on penguins.
Lovely photos. I think most of those are courtesy of Katie Kroger, who's on Zoom. Thanks for that, Katie. So lovely. I plug in. Okay, awesome. First of all, I'm Taylor. Thank you guys all for being here today, whether you're in person or you're on Zoom. I really appreciate your time as I share about the work that I did for my master's thesis, which was, as Gita mentioned, on emperor penguins. And that work is titled Estimating Prey Capture Attempts and Activity Costs in Emperor Penguins Using Integrated Biologging Data. Okay, perfect. So first I want to talk a little bit about foraging in the marine environment. So in the ocean, resources are very patchily distributed. So you have these kind of localized prey aggregations that animals need to be able to find and exploit. And while their kind of like basal energetic requirements are inflexible, conditions in the ocean are highly variable. So in order to be able to acquire enough energy to survive and to reproduce, these animals must be flexible. Additionally, in the ocean, there are somewhat complicated prey dynamics. So often prey items will perform something called a vertical diel migration, where certain organisms will sink lower in the water column and then rise back up in the day or the night, and vice versa. So in order to maximize their foraging efficiency, animals need to maximize the time spent at the most profitable depths and minimize any energy expenditure that they have to use in order to access those prey resources. Therefore, predators must be able to balance the potential energy intake with costs associated with diving in order to access those prey resources. So one way that they do this is by performing a couple different types of dives. And these dive types have access to different prey items as well as different energetic trade-offs. So in the upper part of the water column, the more pelagic part, prey are often smaller. They have less calories per unit item, and they're also more patchy and abundant. Whereas prey in the benthos are often larger bodied and more calorically dense. So these types are often defined by the maximum depth at which a dive terminates and also the depth of that dive relative to the seafloor. So for instance, a transit dive is going to be something that's closer to the surface. An epipelagic dive is going to be shallow but a bit deeper than transit dives. Mesopelagic dives are going to be even deeper. And then those benthic dives are going to be the deepest, and they're going to terminate all the way towards the bottom near the seafloor. Additionally, within each dive, there are 3 distinct phases. So there's the descent phase, where the animal is descending from the surface to depth. The bottom phase, where the animal kind of levels out, and these bottom phases are usually associated with foraging. And then those ascent phases, where the animal is returning to the surface. So in addition to having to be flexible in regards to what prey are available to them, where they are, they also use their past experiences or their behavioral memory in order to shape their foraging decisions. So in more predictable landscapes, they're able to make more decisive sequences of behavior, and in more variable conditions, they have to do more irregular behavior in order to account for the variation. So this is a study that was done in 2022. It was done on harbor seals over about a period of 2 months. So they were able to show that in the top panel, where the harbor seals were encountering more prey, in the next month, the bottom panel, the seals spent more time searching those same areas where the month before they had encountered more prey items. Therefore, memory and environmental context both ultimately influence the dive decision of marine predators. So how do we study marine foraging? One way that we do this is by using something called a biologger or a tag, and these are small animal-borne devices. You can see one on the back of this penguin here towards the back half of its body. And these tags can collect a variation of data. So one type of data they usually collect is depth data. And historically, depth data were used to estimate foraging using things like the shape of the dive, and also these things called wiggles as a proxy of foraging. The wiggle is the actual scientific word for it, and it basically just means the undulation in depth, usually in the bottom phase of the dive. However, more recently, technological advances have allowed biologgers to be used to estimate foraging on an even finer scale. So the tags have extended battery life, they're able to sample at a higher frequency, they contain more sensors, and most importantly, they're able to collect movement data in 3 axes instead of 2. So this high-resolution three-dimensional movement data actually allows us to estimate prey capture in both marine mammals and seabirds. So as a study system, seabirds are excellent because while they forage at sea, they will return to a central location like a colony, which makes them accessible to researchers. Additionally, they often have these kind of life histories where they have extreme periods such as chick rearing that incur increased energetic costs. And in places like the poles, these harsh ecosystems actually further exacerbate those foraging challenges. So for instance, while the regular ocean variability influences their diving, they're also having to deal with different types of sea ice and the formation of sea ice and the movement of sea ice. And all of these things ultimately affect both prey availability. And when the birds are foraging from this central location, like a colony, they're also often experiencing something called localized prey depletion, which is where, especially for non-flying birds like penguins, they're all kind of restricted in this area and they are competing for the same types of prey resources. So the birds have to be even more efficient when they're foraging in these areas. So as a study species, penguins in general comprise about 90% of the avian biomass in the Southern Ocean, so they are a huge part of the avian biomass around Antarctica. They all share the ability to be long-lived, to fast, and to be able to store large amounts of fat. So emperor penguins on the far left, as you can see, are the largest penguin species. They're pretty chunky. They're circumpolarly distributed, so they are distributed all around the continent of Antarctica, and they are actually also the deepest diving seabirds. So these birds have been recorded to go over 550 meters, which is about 1,500 feet. Additionally, they are dependent on ice for part of their life history, which makes them especially sensitive to climate change. And they have this generalist diet, so they can eat fish and squid and krill and all different kinds of things. But this diet does vary by colony. So on the right here, this is a figure depicting the distribution of the different emperor penguin colonies. The size of the circle represents the size of the colony, and the color represents the projected kind of impact of climate change on these colonies. So in red, these are colonies that are predicted to be quasi-extinct by the end of this century. In orange, these are the colonies that are predicted to be endangered. In yellow, you have vulnerable colonies, and then those few green dots are the colonies that are projected to be stable. Here, where the dots aren't so scary, is the Ross Sea. So this area is projected to act as a refuge for penguins that might be displaced from the red colonies that are all around. And here, this small green dot in the Ross Sea is the Cape Crozier colony. And this is where this study takes place. So in the Ross Sea, Parker, who was on this project before me, was able to show that these birds are often displaying distinct foraging strategies. So he showed that there's some birds that are deeper divers, like the birds outlined in red. So these are birds that are foraging more offshore in these kind of gyre systems. And then these birds in the blue are shallower divers that mainly forage on the continental shelf. So Parker showed that the deeper divers overall were making fewer dives per day. So this could be because benthic prey may be more calorically dense, so they might not have to dive as often to hit their kind of calorie requirement, or these deeper dives may be more physiologically demanding, and if you don't have to dive that deep, you don't. And these shallower divers had higher stroke rates. So this is in line with the idea that these smaller, more aggregated prey in the pelagic part of the water column may require more pursuit. So ultimately, we want to take what we know about foraging behavior and link that to the energetics of the birds. So the way that we do this is by using that three-dimensional movement. So that's recorded by accelerometers in those biologging tags. We all actually have accelerometers in our smartwatches and our phones. They're basically just a device that is able to record movement in those three axes. So you have movement forward, backward, up, down, and then sway or side to side. We can also use the information from these three axes to estimate the potential energy expenditure of the bird. So the way that we do this is by using something called overall dynamic body acceleration. That's a mouthful, so for the rest of this presentation, I'm going to refer to that as either activity or oddba. This is just basically the absolute sum of acceleration from all three of these axes. And this is not a direct measure of energy output. There's no calories associated with this. This is basically just a proxy for potential energy output from the bird. And then additionally, in that x-axis, there are these distinct signals in the acceleration that allow us to say this potentially may be the bird attempting to capture prey. So you want to take the energetics of the bird and the behavior and basically put that in context of the environment. So on the right here, this panel on the left is the bathymetry around Antarctica. So you can see it's highly variable. And you want to take that bathymetry, and using that, you can determine kind of how are these birds using the water column in relation to the seafloor. So as I mentioned, at the Cape Crozier colony here in the Ross Sea, that's marked with a red pin. And the red box is basically where Parker saw birds foraging in the 2019 birds, which I'll talk about in a second. But you can see here they have access to multiple different types of bathymetry. So they can go kind of over on the far right on the Ross Bank, that's more shallow. And then between the colony and the Ross Bank, there's also these kind of deeper water areas. This likely means that they have access to multiple prey options. So there's not just one type of prey that they're targeting. So ultimately in this project, we wanted to answer a few different questions. First, how often are penguins attempting to feed? Where in the water column, are emperor penguins mainly foraging? And then what are the different energetic consequences of these different foraging strategies? So the way that we did this was by quantifying the number of prey capture attempts, by categorizing those different dive types in relation to the local bathymetry, and then estimate energy expenditure using activity or oddba as a proxy. So first, I predicted that prey capture attempts would be more frequent during pelagic dives compared to benthic dives. Second, I predicted that prey capture attempts would be concentrated in the bottom phase of all dives. And third, I predicted that activity or oddba would increase linearly with prey capture attempts. So the more often you try to capture prey, the more proxied energy output you have. So moving on to the methods, here's just a short video of a bird looking cute. So how did we collect these data? Birds were captured and instrumented at Cape Crozier in the Ross Sea between late October and November in 2019 and also in 2022. This is the end of the chickering season for these birds. Each bird was instrumented with an AxiTrek biologging tag as well as a radio transmitter. So that radio transmitter allows the bird to be recaptured. These tags are what's called archival, so there's an archive of data on the tag, and you have to retrieve the tag in order to get that data back. How do you tape a small computer to a bird? You literally use tape and glue and zip ties. So these are tags that are temporarily attached to the birds, and they go through something called an annual catastrophic molt, which means every year they molt off all their feathers and regrow them. So nothing is left permanently on the bird. We also collected feathers for sexing, so we were interested in understanding if there was a difference between males and females. And this was work that was done by my colleague, Vicky, whose paper is in review right now, which is really exciting. And in total, we were able to get tags back from 25 birds. So once you have those tags back, you have a lot of data to process. And all this data processing was done in R or MATLAB. And the first step to this is taking that depth data and basically making sure that the surface is correctly identified as 0 meters. So you go through a process called zero offsetting. The depth data was sampled at 1 hertz, so this is 1 depth measurement per second. And the zero offset process was done in a program called ICNOS, which was developed by scientists at UC Santa Cruz. Then you have to find all your dives. So any submersion deeper than 3 meters and lasting between 20 seconds and 30 minutes was defined as a dive. And then every single dive, the 3 phases were identified, and I did this using a package called Tag Tools. Then you have to go through that acceleration data and try to determine what might be a prey capture attempt. So we did this based on a study that was done in 2021, where they were able to validate prey capture attempts in king penguins. So king penguins are the second largest penguin. They're morphologically very similar to emperor penguins. So looking at this figure here, we'll walk through each panel. That top panel is just that two-dimensional depth data. So you can see the bird starts at 0, goes down a little past 150 meters. And in that bottom phase there are those wiggles that I talked about earlier, and those are believed to be a proxy for foraging. The thing about this study was that they were able to validate those prey capture attempts with something called a Hall sensor. So this is a small sensor that's placed on the beak of the bird that allows the scientists to tell when the beak opens and closes. So when you pair that with these distinct signals in the acceleration, you can validate that the bird was attempting to capture prey because it opened and closed its beak, so it caught something. Then you want to take the raw data and you need to filter out some of the noise that's in that signal. So we first filtered out the pitch in the signal, so just the general direction of the bird, and then also filtered out the wing beats. And you're left with this clean signal here on the bottom, and you can use a predetermined threshold to say anything above or below this threshold is likely a prey capture attempt. And again, in this study, they were able to validate those spikes in acceleration above or below the threshold using those Hall sensors. So doing that in this project, the first step was to pair the frequencies of the data. So in 2019, acceleration data were collected at 100 hertz, so that's 100 samples a second. And in 2022, it was sampled at 50 hertz. So in order to compare them, you have to put them at the same sampling frequency. Then you filter the acceleration data, and in this study, we decided to use a more conservative threshold of 0.3. The study in 2021 used 2 thresholds, a more liberal threshold of 0.15, and also this more conservative threshold of 0.3. And basically just said anything above or below the 0.3 threshold, we're going to consider to be a potential prey capture attempt. And then all of those attempts were indexed within each dive to those 3 dive phases. So next, I wanted to know what kind of dives these birds were making. So every single dive was paired to the nearest GPS fix at the location, and then the bathymetric depth there was extracted. And then I used something called percent water column use, which is basically just how close to the bottom did the bird dive. So the 4 dive types that we looked at here were near surface or transit dives, so that's just anything less than 5 meters. Epipelagic dives were considered to be anything between 5 and 200 meters. Mesopelagic dives were anything greater than 200 and having this percent water column use of less than 80%. And then benthic was greater than 200 with a percent water column use of over 80%. So moving on to the statistical analysis. So to analyze these data, I used generalized additive mixed models. Again, that's a mouthful, so I'm going to call them GAMs. And the response variables for the GAMs for my first 2 hypotheses were prey capture attempts, and then for that 3rd hypothesis, it was activity or ADVA. Each model included the following fixed effects. You have dive type, the sex of the bird, year, and then I also was interested in understanding if birds that started out a little bit lighter or in potentially maybe worse body condition would forage differently than birds that started out a little bit heavier. So initial body mass was included as well. In the GAMs, I included a couple different tensor products and smooth terms, and the smooth term that I included was individual IDs. This is just to help account for any individual variation among the birds. And then I was also interested in this idea of foraging memory. So how did the behavior in a previous dive affect the current dive? And so to do that, I included this term which looked at the relationship between the previous dive's foraging attempts and the time that has elapsed since that dive happened and the current dive. The first thing we did was look at those near surface dives, and they had a negligible amount of foraging. So they were excluded from analysis, and so were any non-foraging dives, so anything that didn't have a prey capture attempt. Model selection and evaluation. So this was done using AIC and the double penalty method, and then for all models, the residuals and outliers were assessed. This analysis was challenging, and so this is often how I felt when I was trying to run these models. No penguins were harmed. They're doing their best. So, moving on to the results, these are some of the movements of the birds. So this first batch are the birds in 2019, and then the next batch will be the birds in 2022. So you can see they kind of go all over. Some of them go in one direction, some go the complete opposite direction. You can kind of see the bathymetry a little bit here. So up in that upper right corner, you can see it's a little bit shallower, and then those deeper blue colors are some of the deeper waters. So on average, the birds were at sea for about 9 days. In 2019, the average kind of distance of the trip was 555 kilometers, and then in 2022 is a little bit shorter, around 471. And then we were able to tag 14 females and 8 males, and then 3 birds were unable to be sexed. So in general, birds most often dove pelagically. So of the 23 birds, there were 40,000 dives and over 200,000 prey capture attempts. So here, this figure just shows the y-axis is just the count of dives, and then on the x-axis you have the prey capture attempts per dive. So you can see the distributions of prey capture attempts in these 3 dive types vary. So for the rest of the results section, the dives are always going to be in this order from shallowest to deepest. So it's always going to be epipelagic, mesopelagic, and benthic. So of those 40,000 dives, 44% had greater than or equal to 1 prey capture attempt, and on average, they had about 13 attempts per dive. In general, epipelagic dives were the most common. So this figure shows those 3 dive types on the bottom and then the duration on the left. And you can see that they were the shortest as well. But in 2022, it's a little hard to tell here, but overall they performed slightly longer dives. There was also more data from 2022, so that could be why you see this difference as well. Additionally, this figure shows the amount of time or hours spent on the x-axis, and then these different bathymetric depth bins on the y-axis. And these 2 panels here are foraging on the left in the darker green, and then non-foraging dives in the lighter green on the right side. So in general, more time was spent foraging versus non-foraging, and both these foraging and non-foraging dives kind of show this peak around 600 to 700 meters. But in general, less non-foraging dives were performed in waters that were greater than 800 meters. Additionally, there's this kind of greater distribution of depths in foraging dives. So on the left, you can see that each of those little bars is just a little bit bigger than the bars on the right side. Additionally, this graph looks at the different dive depths within each of these 3 dive types, and then the percent frequency there on the x-axis. So you can see that epipelagic dives were a little bit more evenly distributed across those different dive depths. However, most occurred between 20 and 40 meters, and also this kind of peak here around 120 and 160 meters. Mesopelagic dives also primarily occurred right around 220 to 240, with this peak around 340 meters. And then benthic dives were a little bit more evenly distributed across those depths compared to mesopelagic dives. And similar to mesopelagic dives, there was this peak right around 340 meters. So this figure is a little confusing, so we're going to walk through it. So every single little panel with those 3 boxes is an individual bird. And they're in the order of the dive type on the bottom, in that same order: epipelagic, mesopelagic, benthic for each bird. And on the y-axis are just the number of prey capture attempts per dive. So you can see that there is significant inter-individual variation across the birds. So for instance, overall, epipelagic dives typically have less foraging attempts, but some birds never or rarely dove deep. So some birds never had mesopelagic dives, some never had benthic dives. It just depended on the individual. So moving on to the results of my models. So as a reminder, this first model was trying to understand if there were varying amounts of prey capture attempts between pelagic and benthic dives. And we found that actually dive type alone, so without taking phase into account, there were not differences between the prey capture attempts. So on the x-axis, you have those dive types. On the y-axis, you have those model estimated prey capture rates. And then the panel on the left is data from 2019, and the panel on the right is 2022. So not only did dive type alone not influence prey capture attempts, but neither did initial mass of the bird or the sex of the bird. However, we did see in 2022 there was slightly higher foraging activity than in 2019. Moving on to the second model, so this was, I was trying to understand if you included phase, would there be a significant variation in prey capture attempts across those dive types? And we found that once you did include phase, prey capture attempts did vary significantly across all dive types and phases. So this figure here has those phases on the bottom. So you have the descent phase, that bottom phase, and then the ascent phase. And each panel here are the different types of dives. And then on the y-axis, you have the model estimated prey capture attempts. So you can see clearly here that prey capture attempts were always highest in the bottom phase of the dive. However, there was a higher amount in the ascent phase than I had anticipated, especially in epipelagic dives there on the left. And once you included phase, the effective year became negligible, but there continued to be no significant effect of sex or initial mass. Additionally, this memory term that I had included into this model, we found a significant effect of that foraging memory on the current dive. So in that bottom phase where most foraging is taking place, we found that attempts increased in the current dive when the previous dive had a high number of prey capture attempts, regardless of how much time had elapsed since that dive happened. So this figure is also kind of confusing, so I'm going to take a second and walk you through it. That x-axis there is the previous dive's foraging attempts. The y-axis is the time that has elapsed since that dive, and the colors indicate either a negative or positive effect on the current dive's prey capture attempts. So if you look here in this box, you can see that anything greater than like 10 or 15 prey capture attempts in the previous dive had a positive effect on the prey capture attempts in the current dive, regardless of how much time has passed since that dive had happened. So if a bird's foraging a lot and it comes back up and it takes a break, if it goes back down, it's going to continue to try to forage a lot in that bottom phase of the dive. We also saw significant variation in prey capture attempts over the foraging trip, so over an entire bird's trip, and this was significant for every bird. So here, these individual panels are the birds, and then on the x-axis you have the time since the tag was deployed in days. This is the number of days in the foraging trip. And then on the y-axis, you have that effect on the number of prey capture attempts, with 0 being neutral, 1 being positive, and -1 being negative. If we just look at a couple birds as examples, this bird here outlined in purple kind of has this spike right out the gate around day 1 or 2, and then up to day 5, it's having a positive effect on prey capture attempts, so it's attempting to capture more prey. And then around day 6, it kind of has this drop off, which is corresponding with the end of its foraging trip. And then you have a bird like this outlined in yellow where kind of day 1, it has this big spike in prey capture attempts, and then it kind of levels out as its foraging trip comes to an end. So moving on to my third hypothesis, again, this was a model that was interested in looking at the effect of prey capture attempts on activity or proxied energy expenditure. And I predicted that this was going to increase linearly with prey capture attempts across all dive types and dive phases. And we find that it actually did increase across these different types and phases, but that this relationship was not strictly linear. So this figure here on the x-axis is the total number of capture attempts per phase, and then the y-axis is that model predicted effect on activity. Within each panel, the epipelagic dives on the left, mesopelagic dives in the middle, and the benthic dives on the right, you have the descent phase in the lightest color, the bottom phase in the medium color, and then the darkest color within each panel is the ascent phase. So you can see up to about 30 or 40 prey capture attempts, things are like relatively linear, and you can see that activity or energy expenditure is increasing. And then right around 30 or 40, depending on which dive type you're in, things can get a little bit wonky. So in the epipelagic dives, you either have this kind of dramatic spike, like this one in the bottom phase, or you kind of have this drop off, like in the ascent phase. However, in the mesopelagic and benthic dives, you have this kind of characteristic drop off right around those highest numbers. And this should be interpreted with the knowledge that in those higher numbers, we have the least amount of data. So it's potential that with more data, these relationships would become more clear. But here we did see this kind of threshold right around 30 or 40 attempts. Additionally, there was this effect of memory. So all phases in this tensor product all shared kind of similar relationships. So overall, we saw that if a previous dive had high foraging effort and there was a short break between the dives, there was higher activity or ADVA. So these all look relatively similar, and you can see the most positive effects are in those highest number of prey capture attempts from the previous dive in a short amount of time that has elapsed since that dive. Additionally, this effect of individual ID, so in this, only about half the birds had significant variation in activity or ADVA over time. Again, just looking at a couple birds as examples, you can see here 307B has this kind of, these intense kind of spikes and then troughs, so it has pretty variable effects on the activity over the duration of its foraging trip. However, this bird also had a significant effect of ID, so it looks a little bit more consistent across time or a little bit more cyclical as its trip went on. Okay, moving on to the discussion. So what does this mean for penguins? Why do we care about this? Emperor penguins foraging at Cape Crozier have to balance these really high energetic demands with the harsh conditions that they face foraging in the Antarctic. Over the course of the breeding season, daily food intake in these birds can triple, so they need to consume a lot of food to support themselves and their chick. And at other colonies, one pair of breeding emperor penguins with a chick was estimated to consume nearly a metric ton of prey, so it's a lot of prey items that they're having to consume. Ultimately, understanding the foraging efficiency of these animals and their ability to adapt is going to be key as Antarctic conditions change or deteriorate. And ultimately, we're interested in answering the question, how might this species adapt their foraging behavior in response to these shifting ecological conditions? So here, only 44% of all of our dives contained any prey capture attempts. However, this is in line with other studies that have been done at other colonies. So at the Taylor Glacier and Auster colonies, in about the same number of dives, around 40,000, they showed that only 47% of dives there had prey capture attempts. Birds here primarily foraged pelagically, so only 5.2% of all foraging dives were benthic dives, and this mirrors patterns seen in Ross Sea emperor penguins studied in their post-molt phase. However, off the Adelie land colony, there was a higher proportion of benthic dives in male emperor penguins foraging in the winter, so they had about 32% of their dives were benthic. However, around Cape Crozier, the bathymetry is deeper, so it could be possible that it's easier to dive benthically off of somewhere like the Adelie land colony compared to Crozier. Here, birds spent the greatest cumulative dive foraging over depths between 400 and 700 meters. These birds can only go about 550 meters, so it makes sense that they're going to spend time foraging over areas that they can reach the bottom if they choose to. And then after we excluded those near surfeit or transit dives and the non-foraging dives, we were not able to detect a difference in prey capture attempts across those dive types. It wasn't until we included phase and looked at this kind of more complicated relationship that we were able to detect those differences. So speaking of phases, we saw that the most foraging attempts were concentrated in the bottom phase of those dives. However, there was this unexpectedly high foraging during the ascent phase, especially in epipelagic dives. This is also in line with literature that was done in an isolated dive hole where they equipped birds with cameras and they were able to record when birds were successfully capturing prey. And this was recorded in about 77% of 120 ascents that they were able to record. That being said, those birds were foraging in much shallower depths than the birds in this study. Those birds were only going about 50 meters, so that could be part of it. But likely these birds are feeding kind of opportunistically near the surface where there's better light for them to see by, and also where they're likely encountering these prey that are schooling and abundant. Overall, these different patterns in the dive phases reflect the levels of behavioral flexibility that are ultimately shaped by what's available to them for prey and also by their physiological limits. So in the literature, relationships between activity or ADBA and dive behavior vary in seabirds. So some studies show that with increasing depth, as a bird goes deeper, they're actually using less proxied energy expenditure. And some studies show that there is a positive relationship so that when depth is increasing, activity or ADBA is also increasing. Here we were able to show that activity did increase with prey capture attempts across these dive types, but that this was not a strictly linear relationship. At those extreme values where we had the least amount of data, we saw that there was this potential efficiency threshold. So in like deeper dives, the more prey capture they're attempting, they actually will hit a point where they're not expending more energy to try to capture that prey. Whereas in something like an epipelagic dive, at those highest levels, it's costing them a lot more to continue to try to catch prey. I think my clicker died. So in epipelagic dives, there were these more variable relationships. In those deeper dives, we saw those more predictable and stable patterns. This is also seen in Magellanic penguins, where deeper dives were shown to overall be more efficient. In terms of that memory term that I was interested in, we were able to see that these previous dives influenced behavior in the next dive. So after a short interdive interval or a short break between diving and previous high prey capture effort, we saw that there were more prey capture attempts in the dives that were following. This has also been observed in fur seals. So after successful foraging dives, the fur seals will make a rapid return to foraging. And also in little penguins, where after dives that had prior pursuits, the birds descended at a steeper angle than they did beforehand. Thinking about those inter-individual differences, so differences between different birds, some birds were foraging intensely early on or not intensely, and then others were showing this more consistent or cyclical effort. And similar kind of inter-individual strategies have also been observed in kittiwakes and albatross, different seabirds. And this kind of individual variation likely reflects intrinsic and extrinsic factors, so intrinsic factor like age of the bird or sex of the birds, and extrinsic factors like the size of the colony or the competition for resources. That being said, in this study, we did not find support for any kind of sex difference between the birds. This inter-individual variation is also likely influenced by the prey availability, so what's available around them. And some studies have shown that different behavioral traits of the birds, like boldness, can also influence different individuals. So ultimately, behavioral plasticity and heterogeneity actually enhance a population's resilience, so it's natural selection. Some birds will succeed and others will fail. And these are ultimately limited by both environmental constraints and also physiological constraints. So in king penguins, which again are those birds that are very morphologically similar to emperors, different climate anomalies have already been shown to alter foraging, breeding, and survival. Current climate projections predict that All emperor penguin colonies north of 70 degrees south are projected to be unviable, which ultimately will impact about 35% of the global population. So to discuss some limitations of this study and kind of next steps as I move towards publication, the biggest, I think, caveat is that we were not able to directly validate ingestion of prey items. So that's why these are called prey capture attempts, because we believe they might be attempting to catch prey, but we cannot confirm whether they were successful or not. Additionally, it's likely that these birds are feeding on prey of different sizes, so it's possible that these signals look different for prey of different sizes that we may have missed, or signals may be misclassified. Additionally, only 40% of epipelagic dives included any foraging, so it's potentially possible that some of those near surface or transit dives were captured within that epipelagic category. There's also some limitations to those GAM models. So across the birds, we had different durations that the tags were on, different kinds of levels of data quality, and then some residual autocorrelation within those GAMs. So next, I want to add a spatial context to this study. So looking past just the bathymetry and looking at some kind of metric like move persistence, or potentially using hidden Markov model frameworks. And then also performing these threshold analyses to see if that 0.3 threshold is the most robust for detecting those signals. Okay, that's, I'm gonna move on to the acknowledgements. I'm gonna try really hard not to cry, but I've already cried today, so the possibilities are very low. First, I just want to acknowledge my funding. Geeta touched on a lot of this, but I received money from the Graduate Research Fellowship Program at NSF, CSU PERB, different scholarships from Moss Landing, the Jedi Scholarship, the Wave Scholarship, Ziphius Martin Scholarship, and also from the Coast Foundation. First and foremost, thank you to my advisor, Geeta, and to the entire vertebrate ecology lab. I've learned so much in this process as a scientist, as a person, and I've got to go to Antarctica, and I just had like the most incredible time here at Moss Landing and in this lab, and I feel so grateful. I learned so much. So thank you to all my lab mates, and thank you to my advisor. Thank you additionally to my thesis committee, to Sarah and Danya. They both took a lot of time to give me really valuable, really thoughtful feedback, and this work is better for it. Thank you to the crew of the Palmer, the ship that we were on, as well as our field team, Meredith, Wyatt, and Sarah. I know this is where I'm gonna cry. So sorry. Thank you to Katie and Parker and their baby. They have spent so much time on the phone with me, honestly, like helping me with my models and answering probably kind of dumb questions and just helping me in general, and like are the kindest people and friends and mentors, and I just feel really very grateful to have them in my corner. Oh, okay, sorry. Like have so many more slides. Thank you to all the Moss Landing staff and faculty. Jocelyn, I can't go through everyone on this list, it's gonna take forever, but I just wanna go through a few. Jocelyn, Douglas, so when I started at Moss Landing, I started working here at the front desk in the summer of 2021 before I started school, and this was still COVID times, so it was very surreal. Like the whole building was locked and no one could come in, and it was just me and Jocelyn in like KN95s in the front office, and it was a really weird way to start grad school, and Jocelyn was just so kind to me and really took me under her wing and made me feel really welcome. Sorry. Max Grand was really helpful to me when I wrote my fellowship application, and I think he was like one of the first people I emailed because I was just so excited, and thank you, Max. I feel like without your feedback, I wouldn't have that award, so I didn't learn anything about chemistry from you, but you were my scientific writing instructor, and I just really appreciated your time. Mike Wood, when I got this data, it was about 1.6 billion rows and 100 gigabytes, and I just couldn't even open the files. I was having a really hard time with it, and someone told me to ask an oceanographer, so I went to Mike, and he literally solved my problem in like 2.5 minutes. And was like, oh, duh, just use this file format that I've never heard of. And so I don't even think he knows how helpful he was to me in that process. Chris Mikado, I think some of like the old timers here know Chris, but he is just the kindest man and was so nice to me when I started. He changed my brakes when I couldn't afford a mechanic and is just like salt of the earth. Thank you to Garen and Petra. Thank you to Ivano, to Katie Lage and James and Tara and everyone in IT and everyone in this photo. In general, Moss is just like the best community, and I feel so grateful to have been a part of it. Okay, thank you to Spencer and Ollie and my cats. I found like the grumpiest pictures of them I could find. They're like my emotional support animals against their will, but I'm so grateful to have had them, and to my grandparents, my grandma, and okay, I can't even say their names, but I love them. Thank you to the best friends in the whole world. I had so many pictures, I could not even fit them in here. And I tried to write everyone's names, and it got really silly. So I just tried to put everyone here. I'm so grateful. This was like the biggest group of friends I've ever had, and just such like a wonderful, supportive group, and such kind and smart and supportive people. Okay, I'm almost done. Thank you to all my Oregon friends, to my PhD advisor, Josh Dewar, up in the upper left. As Gita mentioned, I've been double enrolled for the last year as a master's and a PhD student, which I do not recommend. But my advisors, both of them, have been so supportive and patient with me and helpful to me in this process. And to all my wonderful friends in Oregon, it's just such a great group of people. And then in August, I was on the Sikuliak, which is a research vessel up in the Arctic, and I was literally finishing my thesis like on a boat in the Chukchi, and it was really weird. And all these scientists here on the left and all the crew on the Sikuliak were so supportive to me and so helpful, and I just felt really grateful to be like sending this email in and being in this amazing place with these great people. I am done crying. Thank you so much to everyone for listening. As Gita mentioned, I'm now at Oregon State doing my PhD. I'm doing something in a similar vein of predator-prey dynamics, but I switched away from birds, and I'm doing large whales. You can find me on GitHub. All this code will eventually be posted. I also have a website, and I also host a podcast that focuses on graduate student research at Oregon State. So if you're interested in learning about different kinds of research, not in California, sorry, you're welcome to listen anywhere you find podcasts. And I'll take any questions. Thank you. I have makeup on my face. Okay.
So that was a great job. Do we have any questions for Taylor?
Congratulations, Taylor.
Thank you.
I have a question. So the whole project is kind of focusing on energy use and how it relates to diving and why do they dive and when are they actually catching prey. And when you mentioned that 44% were foraging dives or where there are prey capture attempts, and that's only half the time, what's happening the other 50% of the time? Is it just exploration? Do they do other things underwater, or are those things we're still trying to figure out?
Yeah, that's a good question. I believe a lot of it is searching. I believe they spend a lot of time trying to find those prey resources that, as I mentioned, are very kind of patchily distributed. I think people always ask me if they could be like running away from seals and avoiding predation, and that's definitely possible. They do get predated on, so maybe part of that is they're having to go deep to try to get away from things or to move somewhere else. I'm not entirely sure, but I'm assuming searching behavior, searching for places to forage, or potentially avoiding predation. Thank you for your question.
Congratulations, it was a great
Thank you,
presentation.
Duncan.
So I'm curious, you showed some variation in the overall activity over the course of a foraging trip. Do the penguins, as they accumulate food and more mass in their body, is that impacting their metabolic rate as they start digesting? Are they putting less effort into foraging because they have more food in them? Is that part of it?
Yeah, that's a great question. I can't speak to their metabolic rate. That's not something we're able to measure, but I think like there's only so much food that they can carry, and they are trying to take food back to their chicks. So, you know, it's one thing to like catch a bunch of fish in the beginning, but then you digest it all and poop it out, and then you can't take it back to your mate and your chick. So I would assume that there's only so much fish or whatever that they're eating, and so they kind of hit this limit of like, oh, I'm full. Okay, maybe I can go back now and not have to stay out for 14 days or however long they'll stay out for. Thank you for your question.
Use the mic. Make sure you actually put it close to your mouth.
Great job, Taylor. That was awesome, and you made a really good job of like making things simple when they are not so simple.
Yeah, thank you.
So my question's kind of like related to something you mentioned in the intro. You were talking about wanting to capture the energy expenditure that they have, and you did that great through the ODBA. But were you able to kind of calculate like energy acquisition? I know it might be difficult without the prey types or so. And then maybe how that changes based on foraging strategy, if it's epipelagic, meso, or benthic.
Yeah, so we, again, like can't, let me go back to a figure. We can't directly kind of, oh my gosh, sorry. We cannot directly estimate ingestion. So like we don't know if they're actually catching anything. Like they could just be trying and they can't get anything, and it's hard, and it takes a lot of attempts to actually catch an item. Excuse me, but in this figure here to kind of address what you said, so if, let's say that they're successful every time, which they're probably not, but let's say they're successful every time. So in those deeper dives, they're catching, in theory, a lot more than they are in those epipelagic dives. And that could be because when you go deep, you have to really use your time that you have down there. Whereas when you're closer to the surface, you can eat a couple things and pop up and start over. But if you're going deep, it's costing you, and you have to make use of the time that you're down deep. So even though epipelagic dives have the least amount of prey capture, we also saw that they're the most frequent by far. And so they're performing epipelagic dives a lot more. And in my mind, this is not like science, but in my mind, I believe that they're trying to just equal it all out, so that if they're going epipelagic, they're doing it X many times to get the same amount as birds that are going deeper and eating similar amount, because they all are kind of similar size and need kind of a similar amount of resources. I hope that answers your question. Thank you.
Nice work, Taylor.
Thanks, Max.
I actually have a chemistry question for you. No, I'm kidding.
No.
So I have a question from a chemist about penguins, pretty
Okay.
much. So I understand that they spend quite some time quite deep when they're like foraging in the benthic. So, and my question is, how do they see what they capture? Like, how do they ID those preys and actually catch them?
Yeah.
And could that be that they're just searching around and moving around, giving you all those bottom returns you show on that plot here? I'm just curious, pretty much.
Yeah, I don't know how they see. I mean, they don't. Like, there's no light down there. That's below the photic zone. So they are, I don't think, able to catch things by sight. I'm not sure exactly how, but I think they're using a different sense in order to feel movement, or maybe they just kind of know where these benthic
Actually,
creatures.
they think they are visual predators, and they're probably using bioluminescence.
Oh,
So,
okay, that's a way cooler answer. So.
sorry, I was like, normally I have that, but I was like, oh, this one, they
Yeah.
do think that they are visual predators,
Yeah,
and that
okay.
it's primarily bioluminescence.
Yeah, cool. That's yeah, a way cooler answer. So they're using bioluminescence. What else?
All right, well, if that is all the questions, we will let her go and give her another round of applause.
Thank you.
simple. Oh, yeah. What? There is. We're gonna steal her away for like a half an hour, and then